Hello and welcome to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Quentin, and I'm joined by Dr. Elena Hyde, and will be your host this evening. We are broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts every Monday night at 9 p.m. local Toronto time, or Tuesday morning at 1 a.m. Universal time. The York Universe production works in concert with our online public viewing program run by the Observatory team, which runs between the hours of 9 p.m. and 10 p.m. local Toronto time. Go to www.yorku.ca/science/observatory and follow the links to OPV, online public viewing, to join the chat. You can always connect with us on Twitter with our handle @YorkObservatory or Instagram with the handle @YorkUObservatory and Facebook at Allan I. Carswell OBS, OBS. All of our programs are free, but if you would like to make a donation, again, see our website at yorku.ca/science/observatory. So, Dr. Hyde, what's the weather like right now for you at York?
Well, I don't think we'll be doing any direct live imaging tonight, unfortunately, but you can, of course, as you mentioned, count on our wonderful online public viewing or OPV crew to be showing beautiful stock images available from the telescope. If it does, of course, clear, there are some lovely things to see out in the sky. We just have to, of course, get the clouds to move. Even if you have even partial clearing anywhere near Toronto, I'm sure that most of you can probably see Jupiter. Jupiter is very, very bright. And actually, if you're listening live, looking outside right now, it's actually, what is it about? Several degrees above the horizon, and it's 50 degrees above the horizon, so you can see it nice and high in the sky, very, very bright, minus 2.71. So at this time of year it has occasionally been mistaken for an airplane, but it is one of the brightest things that you can actually spot in the sky at the moment. So if you are out with any kind of clear weather, the moon and Jupiter are the way to go. Unfortunately for our live imaging, we're not actually able to open up the telescopes tonight.
Yeah, and speaking of things that are minus 2.71, the temperature out where I am is about -3 degrees. So if you do decide that you want to try your luck and do a little bit of stargazing tonight, if you want to try to see Jupiter,
stay warm.
Stay warm. Make sure you dress for the weather, because we are certainly entering winter time. I don't know exactly when the first snow will be, but I guarantee it'll be any day now.
Yeah, we've seen a lot of frost, and I think, a little bit farther north of Toronto and, maybe Northern Ontario, they've had a bit more than frost. So we do have to watch out for the snows, as you say. And it is one of the dangers, of course, of winter astronomy is beautiful long nights, but it's pretty chilly. So sleeping bags and snow pants and all that good stuff, definitely recommended.
Absolutely. Always make sure to dress for the weather and know what it's going to do.
Well, if we knew, absolutely.
Yeah, I mean, to the extent that anybody can know what the weather is going to do. It's always it's never fun to get all prepared, take your telescope out, and then it rains all night. You can't even take the thing out of storage. So it's always
exactly.
Always important to check the weather report.
and if it says storm, just stay home.
Absolutely.
Well, hopefully we'll get some more clear nights up ahead, and I'm hopeful that we're able to do actually some very clear faint object viewing later on this winter, maybe after the classes end at York. It's a very fun time of year for us at the observatory because there's a lot less class observing when everyone's off on Christmas break. So we can observe all kinds of fun, interesting dim objects if we want to. I think we'll be talking about one of those later on for a news item. So,
ooh, exciting! All right. Well, do you want to get into the history?
Yes, well, let's do that. Let's travel back in time, if you will. With sort of starting off a little bit of a theme. Some of you listening to this show will have heard about black holes, mysterious objects out there in the universe and even in our own galaxy that are sort of infinite, well, thought to be perhaps infinite points of space-time and pulling, into a singularity. Nothing escapes. Very sort of science fiction, usually associated with kind of modern physics. However, I am going to take you all the way back to November 27th. So 7 days from now, back in 1783. That's right, 1783. So this was a paper by a scientist and well, philosopher and clergyman, John Mitchell, who actually put out a publication um, predicting black holes. So yeah, this is he was sometimes called a country parson, and he announced his idea in 1783. He was an English country parson. He was a incredibly brilliant and original scientist by all accounts, but he did not really promote himself, which is an unfortunate aspect of science. In that, if you don't promote yourself and no one else helps, your ideas can remain largely unknown. And that is actually what happened to John Mitchell. So I figured this would be a great time to start off with some modern ideas. But back in 1783, he was born in 1724, studied at Cambridge University, and he was very accomplished across many fields of not just science, but also language. He taught Hebrew, Greek, mathematics, geology, and this was 1724, remember, so this is some time ago. There's no portraits that have ever been recovered, at least none that I could ever find, of Mitchell, so John Mitchell. He has a description that was written about him as a quote unquote, a little short man of black complexion and fat. And that's actually the quote that they gave to this very well accomplished scientist. So he
not exactly flattering.
No, he did not really promote himself at all, but his incredible ideas and contributions meant that he had numerous scientific visitors when he was at Leeds in England, including people like Benjamin Franklin, who was very, very good at promoting himself, the chemist Joseph Priestley, who discovered oxygen, the physicist Henry Cavendish, who discovered hydrogen. And it's worth putting into a little bit of a timeline. In 1766 was actually when Cavendish discovered hydrogen. So a few years later, 1778, it was discovered that air was composed of nitrogen and oxygen. 1781, Priestley manages to create water by igniting hydrogen and oxygen. People were just realizing what atoms were, and things like nitrogen, oxygen, hydrogen were basically just getting started. It wasn't until 1800s that atomic ideas even came into play. And so you had, of course, electrolysis and the photovoltaic effect in the 1840s and so. And finally, it wasn't until 1871 that we finally got Mendeleev's periodic table, and people like van der Waals and Balmer predicting energy levels transferring and things like that. And it wasn't until 1897, so much later, that we've actually discovered things like subatomic, I suppose I should say atomic particles, like electrons, protons, neutrons. So the electron was discovered in 1897, and this was 17 24, he was studying, and he announced his ideas in 1783. So this is actually pretty foundational, important work that Michel was doing. In 1750, he showed that magnetic force was exerted by each pole of a magnet, which was a groundbreaking idea. He showed that the force decreases with the square of distance, which is now learned by all beginning physics students. So you can thank him. He actually wrote a book after the catastrophic Lisbon earthquake of 1755 that helped establish seismology. He suggested that earthquakes spread out as waves through solid earth. He built the apparatus to measure the force of gravity. And Cavendish, who carried out the experiment after Michel's death, is usually the one who gets mentioned in papers, but Cavendish did, to his credit, actually try to give Michel credit for the idea. The fundamental physical quality called the gravitational constant that we use everywhere in physics. I mean, maybe not quantum mechanics, because quantum mechanics and relativity don't necessarily always agree. But thanks to Michel, Cavendish was able to calculate the mass and average density of Earth. So Michel was doing incredible stuff. He applied new mathematics of statistics to astronomy, showing how many more stars appear as pairs or groups that could be accounted for by random alignments, and actually made an early argument for an abundance of binary stars, which is true. There are more binaries in multiple stars than there are single, and he was able to do this with statistics, studying how stars are distributed on the sky. And of course, finally, the one that I'm mentioning here today was he actually came up with the concept of existence of black holes, and this came to him in 1783, and he was looking at a hypothetical method to determine the mass of a star. So at this point, he had some Newtonian physics, and he had Newton's theory that light consists of small material particles. And so he used the particle theory of light to reason that if these particles were coming out of the surface of the star, they would have their speed reduced by a star's gravitational pull. Like, just like Earth has gravity, a big star could pull light particles down. So just like projectiles fired up from the Earth. So he actually made this analogy, which is a very, very good one. And by measuring the reduction in the speed of light, or redshift, from a given star, he thought it might be possible to calculate the mass. That's not really how that works, but they had a very close to the right idea. And if you keep going along that line of thought as he did, he can ask the question, what would happen if a star's gravity were so strong that its escape velocity exceeded the speed of light? And this is exactly what happens in a black hole. And Mitchell realized that light would have to fall back to the surface. And at this point, he actually knew the approximate speed of light. This was found by I'm not sure I'm saying it right, but Ole Romer, and who actually was a Danish astronomer in the 1600s, 1644 to 1710, I believe. And in the 1676, he made an early measurement of the speed of light. It might possibly be the first one. So Mitchell used this early speed of light and calculated that the escape velocity would exceed the speed of light on a star more than 500 times the size of the sun, assuming the same average density. And then, therefore, light would not be able to escape and would be invisible to the outside world. Today, of course, we would call it a black hole. And this is the right answer, but he, of course, was wrong about a few things. So we know now from Einstein's relativity of, I might add, 1905, which is several hundred years later. So quite a ways in the future, Einstein's theory of relativity, 1905. We know after that light moves through space at a constant speed, regardless of the local strength of gravity. So that's why I say, you wouldn't actually get a reduction in speed. It's really a change in the frequency, so you get a redshift. Mitchell's proposal to find the mass of a star by measuring the speed of light wouldn't have worked, but he's absolutely correct in pointing out that it must be invisible if its escape velocity exceeds the speed of light. This was obviously very, very far ahead of its time, made very little impression at the time, actually, and was not rediscovered until 1916, after Einstein published his theory of gravity. Of course, after Einstein came all kinds of interesting things. You had the Karl Schwarzschild solving Einstein's equations for the case of a black hole, which he imagined as a spherical volume of warped space. And you had all kinds of sort of explosion in I suppose, black hole physics. Of course, we know now that black holes can get absolutely huge, and in theory, we can have black holes in any size. So this, is simply proportional to its mass. A black hole with the mass of the Earth would be about an inch across, or a marble. One with the sun would be a black hole. The mass of the sun would be a few miles across. And if you had a black hole with the total mass of the entire Milky Way galaxy, everything you can see in the whole night sky, you get a black hole of about a light year across. We know this now. Obviously, in the 1700s, Mitchell did not know this. He suggested that we might be able to detect invisible black holes if some of them had luminous stars revolving around them. This is actually one of the methods used by astronomers today to infer the existence of black holes. So this was really an early conception of black holes in 1783. Very few scientists in the world, well, I would say maybe none, were actually mentally equipped to understand what he was talking about. Nobody was able to understand it because they didn't have relativity, and the concept sank into complete obscurity and had to be, of course, rediscovered. But it is absolutely astonishing that he was able to do this as a natural philosopher in, studying astronomy, geology, optics, gravitation, and the name John Mitchell should absolutely be remembered for his, one of the great unsung scientists of all time. So I just thought this would be a fun way to start off. Back in 1783, John Mitchell anticipates black holes, November 27th.
Absolutely. That's really fascinating. And it dovetails really nicely with what I wanted to talk about.
I know. That's why I picked it. So speaking of black holes.
Yeah, speaking of black holes, as Elena was foreshadowing, I would like to talk about November 21st, 1905, which is when Albert Einstein published his famous E=mc² equation. So November 21st, 1905, the German physics journal, Annalen der Physik, published an Einstein paper that would go down in history. And its title in English translates to, "Does the inertia of a body depend upon its energy content?" So this is the paper in which Einstein deduced his famous equation, E=mc², which says that mass is equivalent to energy, and it's possible to convert from one to the other. Certain nuclear reactions are capable of generating immense quantities of energy, far more than can be achieved through chemical reactions, because they convert the mass of the reactants directly into energy. So the factor of c² means that even a gram of mass is equivalent to nearly 90 trillion joules of energy. So the equivalence of mass and energy actually follows as one of the consequences of the theory of relativity, which Einstein had written about for the first time only a few months earlier. His paper on the electrodynamics of moving bodies was published on September 26, 1905. And this was the first description of what we now call special relativity. It explained that distances and times are different for objects moving at speeds close to that of light. And it laid the groundwork for a revolution in physics that completely changed how we understand the universe. Now, special relativity was really only the appetizer for the much broader theory that is general relativity, which describes gravity on the most fundamental levels, and really put a rigorous theoretical framework to the phenomenon that John Mitchell had anticipated way back in the 1700s, which are black holes. But nonetheless, you can see how the ideas were there in 1905 and how they would eventually lead to Einstein's full treatment of relativity, which I believe came out in 1916, was his paper on general relativity. Anyway, it seems crazy.
Yeah, I think that's about right.
Yeah, it seems crazy, though, that Albert Einstein would end up publishing two groundbreaking papers like this so close together, both of them in 1905. It's actually even more of an accomplishment than that. Einstein's paper on the photoelectric effect, which ended up earning him the 1921 Nobel Prize, was actually published on June 9th, 1905. This paper proposed the idea that light can only be absorbed or emitted in discrete packets called quanta, which laid the groundwork for the entire field of quantum mechanics. And on July 18th, Einstein published another paper that explained that the phenomenon of Brownian motion was evidence for the existence of atoms. So all four of these papers were extremely important with massive implications for the future of physics. And as a result, 1905 is often referred to as Einstein's Annus Mirabilis, or miracle year. Just absolutely fascinating quantity of work that came out of this man during this year.
Absolutely, and it is worth noting as well, like as you say, Einstein did produce some amazing papers, and there were so many people involved for so many literal hundreds of years before Einstein, getting around and picking up sort of pieces of various aspects of what he would later put together, right? As you say, we had the early speed of light calculations, the early atomic experiments, the early idea of a black hole, and it was still Einstein that put it together, but it was such a large and dynamic community of scientists. It's worth thinking about as sort of a maybe not necessarily the top of the iceberg, but an amazing conjunction of being able to put together all this material in a way that really launched the next generation of physics. Very fun.
Absolutely. Really, the early 1900s were kind of the watershed moment. I remember, I forget who it was. There was one physicist who was on record saying around the turn of the century that they had solved all of the major problems in physics, and now it was all just a matter of bookkeeping and putting the finishing touches on the theories. And then within a couple decades, you have all these discoveries in relativity, you have all these discoveries in quantum mechanics that are just completely upending our intuitive way of understanding the universe, and leading the way for all these new discoveries and all these new technologies, which we now rely upon in order to live on a daily basis. It's just incredible time for physics.
Yeah, exactly, and it is interesting. You mentioned the quote, "There is nothing new to be discovered in physics." There is a misattribution. So Lord Kelvin, I believe it was, it's the Northern Irish physicist and mathematician William Thomson. He's also known as Lord Kelvin. It is a misattribution that he said that quote, but actually he didn't. And the actual origin of it is something of a little bit of a mystery. as far as I
Oh,
can tell. So I was actually unable to. I did a little looking around earlier for a different episode that we did on this show actually, and I couldn't find out who the quote uh, was actually from. So
maybe it's
it wasn't Lord Kelvin, but there was a lot of, shall I say, animated
hmm,
discussion and people trying to put themselves forward in the scientific community. So for the same reason, John Mitchell did not get much credit. He did not put himself forward. A lot of other people would either put themselves forward or try to kind of, um, you know, maybe say things that weren't necessarily accurate. And so there's a little bit of I believe, politics as well between the different labs that were happening, and of course, Kelvin being very, very famous for his, his thermodynamics, um, but he did apparently have some interestingly wrong predictions about flying being impossible,
oh
but
yeah.
it's a phrase. I think uh the no the no more discoveries in physics phrase is one of those ones that will probably remain a mystery for a while.
Oh,
Um,
okay. I did you want to talk about the next one? This is interesting because this is also someone from
yeah,
that
on
earlier
the
period of
same vein as
physics.
we've been discussing.
Yeah.
So as you mentioned, in 1905, Einstein did have an amazing set of papers which put together so many ideas and of course added a tremendous amount from his own. Leading up to that, there was another pretty important discovery that I mentioned briefly before when I talked about John Mitchell, is the van der Waals, actually. So we'll just do a little bit of a timeline. So in 1783, John Mitchell is established and anticipating black holes. So, you know, a little over 100 years later, Einstein publishes his paper, 1905. But in the meantime, in 1837, we had November 23rd, the birth of Johannes van der Waals, who was a Dutch theoretical physicist and thermodynamicist, famous for his pioneering work on the equation of state for gases and liquid, and especially water. Water is some strange stuff. So I thought this would be a good one to add in because, of course, van der Waals, was also part of this scientific community, such as it was, so I say. And he was born in November 23rd, so 3 days from now, but back in 1837. He started his career as a school teacher and became a physics professor. And I believe he was one of the first, or perhaps even the first physics professor of the University of Amsterdam. I'm not entirely sure, but he did win the 1910 Nobel Prize in Physics for his work on the equation of states and gases and liquids. He's primarily associated with the van der Waals equation of state, which describes gases and their sort of condensation to liquid phase. He also has a force named after him, the van der Waals force, which is between molecules. And there's a lot of his I think, discoveries named after him. Throughout what we now call sort of chemistry and thermodynamics. And James Clerk Maxwell, famous for Maxwell's equations, this was a fellow who has some good quotes associated with him. There's no doubt that the name of van der Waals will soon be amongst the foremost in molecular science. And both James Clerk Maxwell and van der Waals also did a fairly good job of getting themselves out there and well known. So in 1873, so he was in his 50s, he wrote a thesis which noted the non-ideality of real gases. And he started writing down how molecules might interact, introducing things that people who've studied thermodynamics might have heard of, like the equation of state. How does a solid exist? How does a gas exist? How does a liquid exist? What makes a liquid turn into a gas? What makes a solid turn into a liquid? And of course, actually being able to write down a physical relationship means that material sciences after van der Waals was revolutionized. Molecular physics hugely changed, and being able to manipulate fluids and liquids and create what we would call modern materials. It was what I just can't even say how much of a impact it has made on physics, but especially thermodynamics. And in the when he derived the equation of state for basically molecules, his work actually showed that there was a model in which the liquid and gas phase of a substance can merge into each other in a continuous manner, showing that the phases are the same nature. So this basically assumed that molecules existed. And if you remember what we were talking about in the timeline of physics, people discovering that things like hydrogen and oxygen existed was kind of a new idea. It was somewhat debated about whether or not atoms actually existed. If molecules existed, what would they be? So there wasn't any way to quantify it before he came out and started publishing it. So it's been some very, very successful scientific career. And of course, he received numerous honors and distinctions. Besides winning the 1910 Nobel Prize in physics, he got many honors and doctorate. He got an honorary doctorate. He was, member of course, several Royal Academies, and there actually managed to be a minor planet named after him. So if you're interested, it's planet 32893 van der Waals is actually named in his honor. So it's a bit of fun as well. And really, I think, for a someone born in 1837, he was the originator of modern molecular science. And depending on how much everyone liked their thermodynamics classes, you can also blame him for that. It's been one of my favorite things to look at was pressure, temperature, and volume, and how that affects substances in our solar system has always been just fascinating to me. So PV equals nRT, and it's just the tip of really what he managed to accomplish. He left his posting as a physics teacher once he got his professorship at the University of Amsterdam, and because of his scientific contributions, he went on to get things like the law of corresponding states, which is a theory showing how hydrogen and helium can become liquids instead of gases. And this led to this discovery of superconductivity in 1911, or the idea of superconductivity in 1911. So there's this really fun, you could read a lot about it. I could probably talk about him for a whole hour in and of itself. But he did have a bit of a very different science track than than John Mitchell in that he had incredible success. He was very widely known, and he lived until the ripe old age of 85, and by all accounts, did very, very well in terms of getting quite famous. So, so I think I'll just go ahead and leave with this quote from him. So this is actually a van der Waals quote. It will be perfectly clear that in all my studies, I was quite convinced of the real existence of molecules, but I never regarded them as figments of my imagination. But when I began my studies, I had the feeling that I was almost alone in holding that view. So you do have to be a little bit stubborn to do this sort of thing, I suppose.
Yeah, I know that molecules were a really controversial topic when they were first being suggested. My understanding is that didn't a lot of physicists kind of treat them at the time like, oh, this is a useful tool for simplifying the equations, but they're not like a real thing.
Yeah, it would be at best an approximation, but surely that wouldn't be actually what was happening. I mean, atoms don't just stick together. That would be crazy. So
little did we know that all of chemistry is atoms sticking together.
Yeah, and I mean, of course, he did have some support from earlier studies, but pushing back against the established view is a very, very hard thing, especially when you don't have a lot of support, and nobody starts out famous. So it was if you go back to the 1700s, you can find early discoveries from atoms and things like that. Of course, Cavendish's hydrogen studies that I mentioned before started with John Mitchell, and of course, if you've got hydrogen, and in 1800 they already knew that they could separate water into hydrogen and oxygen. So we knew that could happen, but getting people to actually accept the idea of molecules was a very different beast.
Speaking of, I guess, big moments in our scientific understanding of the universe, I've got a bit of a milestone as well. This one is the November 19th landing of Apollo 12 on the moon. So not exactly the first step of human beings on the moon. That was Apollo 11, which was a few months prior to this. Actually, Pete Conrad, who was one of the astronauts on this mission, even had a little bit of a quip about this. He said he was the shortest man in the initial group of astronauts. And he riffed off of Neil Armstrong's "One Small Step for Man" quote. He said, "That may have been a small one for Neil. That's a long one for me." As he stepped off of the lunar module. So yeah, this mission it did land on November 19th, 1969. It landed in the Ocean of Storms. It had launched from NASA's Kennedy Space Center 5 days earlier on November 4th, and it carried 3 people. Charles, aka Pete Conrad Jr., Richard F. Gordon Jr., and Allan L. Bean. Apollo 12 was the second crewed mission to the moon. Apollo 11 had only launched a few months earlier in July, and they landed within walking distance of the Surveyor 3 robotic probe, which had been launched in 1967. And this demonstrated that NASA had the capability to perform a precise landing at a given target location. This wasn't, Pete Conrad's little quote when he was stepping off of the module. This wasn't the only aspect of this mission that I found kind of humorous. For example, Allan Bean, that Apollo 12 was equipped with a color camera that would allow it to take better quality television pictures from the moon compared to Apollo 11. Apollo 11 could only broadcast in black and white, so all of the old footage we have of the moon landing is in a monochrome. But Apollo 12 was equipped with a color camera, and the idea was that it would be able to take better quality images. Unfortunately, Alan Dean ended up accidentally pointing at the sun when he was carrying it to the location where it would be set up. And this ended up damaging the camera, and it cut the coverage off almost immediately. So the rest of the mission was done, I guess, outside of the eye of the public, unfortunately. But there were some important activities that were performed. For example, the deployment of the Apollo Lunar Surface Experiments Package, or ALSEP, which was a set of nuclear-powered scientific instruments that continued to collect data about the lunar environment long after the astronauts left. The subsequent Apollo missions that made it to the moon, which was Apollo 14, 15, 16, and 17, they also left their own ALSEP packages. Apollo 11 hadn't done this because of the risk of an early abort to the activities on the moon. So instead, they left behind a smaller package called the Early Apollo Surface Experiments Package, whose instruments could all be set up in 10 minutes or less, just in case they needed to leave rapidly. The astronauts also collected many samples from the surface. They performed 2 EVAs, and they were able to find ejecta from Copernicus crater inside Head crater, which is 230 miles to the south of Copernicus. And they found samples. They found that samples of these ejecta were later used to date Copernicus crater to 810 million years old. After spending around 32 hours on the moon, the lunar module launched back into orbit, and it docked with the command service module 3.5 hours later. The crew returned to Earth on November 24th, 1969, 10 days after launch. And that was the second mission to the moon.
Very nice. And, of course, Apollo 12, like a lot of the missions, does have a really nice archive. So if you are interested to see a few of the recorded videos that are publicly available, there's actually an Apollo 12 multimedia site on the NASA history.nasa. And they do have a section that's actually called "That Might Have Been a Small One for Neil." Like that's actually what it's called on the official NASA website. And they have a whole bunch of video clips and sort of text transcripts of what they were saying. They do actually have some orientation tutorials as well. But yeah, as you say, they have highlighted, I suppose, a lot of things you were talking about, Quentin. They have one that's called TV Troubles. And the main sections for Apollo 12 are a visit to the snowman, that may have been a small one for Neil, TV Troubles, and Wake Up and EVA2 prep. So as you say, they were definitely having a lot of fun with it.
It's really interesting. They spent 32 hours on the moon. That's more than a full day. So they did sleep inside the lunar module on the moon's surface. I wonder what that must have been like, trying to sleep under those conditions.
Well, I think it's probably easier. I mean, I've heard, obviously I haven't got to go to space, but they say that it's very easy to sleep in space because of the low gravity. So it might also be easy to sleep on the moon.
And I suppose we'll only know. There's only one way to really find out.
I know, right? We just have to go there. Somebody send us. So shall we, before I go on to a slightly more recent launch, do you want to do the
final
oh no, I was just going to say, do you want to do the I'm forgetting my words now, the sound bites?
Oh yeah, sure, absolutely.
Since we're more than halfway.
Yes, yeah. I did want to remind the guests, this week we have our Wednesday tour that is going to be beginning at 6 p.m. Remind me, Elena, how long is it going to go?
I believe this week it's only from about 6:30 to 7:30, so it's a little bit of a shorter tour. But the best way to get there is to go ahead and go to the website, yorku.ca/science/observatory, and click on the free ticket link and just go for the time slot that your ticket says. That's the best way to make sure that you get a free tour. So we are back with in-person tours again this Wednesday, just a little bit later than last week, but next week we'll be back at 5:30 again. So just make sure you check the website and read the start time on your ticket.
That's so exciting. Yes, it is. It is important that folks do get a ticket, even though the tours are free. This is just because there's safety limits to how many people you can have in the dome at a given time. So we don't want to overcrowd that place.
All right. So do you want to do the sound bites or shall I?
Yes, absolutely. So once again, folks, for anybody just tuning in now, you're listening to York Universe, which is broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. If you want to join us in the chat or ask any questions, please go to our website at www.yorku.ca/science/observatory. You can also follow us on Twitter at YorkU Observatory. So tonight you're listening to Quentin and Elena, and we are currently discussing the historical events that happened this week. We've just talked about the Apollo 12 mission, which was the second crewed mission to the moon. You should swing by our website and click on OPV on the menu bar to join our chat and take a look at some of the brilliant pre-captured images from our observatory that we are sharing with you. So yeah, I believe those are all of the announcements that we have for the midsection of the broadcast. Elena, did you want to talk about the space launch system?
Yes, I did actually. So, I think it goes well with our show for tonight. We sort of talked about a lot of the foundational physics, and people say, "Oh, what can physics get you?" Well, physics is what got us all the way to, as you say, Apollo 12. Without all of the physics discoveries that had led up to that 1969 mission, we wouldn't have had the material sciences to even create the Apollo 12 rockets. And of course, if we're going to talk about the moon, and this week in space and astronomy history, I'm going to go super recent and actually just go very, very, very recently, 2022, which by my count was last year. Still, almost 2 years ago, if I wait a couple months. No, November 16th, 2022. So very recently, we add the SLS, or Space Launch System, November 16th, 2022 at 1:47 a.m. Eastern Time, carrying the Orion spacecraft on the Artemis 1 mission, which is our 2022 attempt to start getting ready to potentially one day actually maybe go back to the moon. And if we get there, then hopefully Mars as well. So after the Apollo program ended, it really the human space exploration with actual humans took quite the downturn. And it's only very recently, in the last 2 or 3 years, that we've actually seen modern capacity go up to the point where we could go to the moon. And it's been very exciting for all of us who are interested in, of course, human space exploration, but also rocketry and the space launch systems that are out there right now. So this particular mission used something called SLS, which is literally just Space Launch System. It's made by the US. It's a super heavy lift but expendable launch vehicle. This is the primary launch vehicle for the Artemis moon landing program. Artemis 1 was the real kickoff to this program. So in Artemis 1, we finally saw a moon orbiting mission with not a crewed spaceship, but a spaceship that could hold a crew if it had a crew in it. So this was a test of the system, and it was delayed a few times. It was a lot of nail biting happening, but it did succeed. This was the first integrated flight test with the Orion spacecraft, which is the partially reusable place where the crew would go. So this is where your crew would live if you had a crew, and you've got your crew module, and there's actually a European service module as well in the Orion spacecraft, and that's then attached to your Space Launch System, or your SLS. This is in contrast to things like the private space launching systems. Like, of course, you have the newest and the greatest this year is the Starship launches by SpaceX. Their last one had several minutes before it exploded. So there's definitely some private sector strong competition, but the government made, or I suppose government contracted SLS for Artemis is still their main vehicle. Now, as I say, I tried to emphasize not reusable, because as a direct contrast to things like SpaceX, once this goes up, that's it. That you're not going to be reusing any of this except for perhaps your Orion component. NASA, has worked with several different contractors, and the idea is that they're going to continue with the Artemis program. The Artemis program having had a successful flyby the moon. So the spacecraft went up, it went around the moon successfully. It did exactly what it was supposed to do. They ran a whole bunch of tests. They had robots and mannequins on board. So they're human stand-ins basically, but according to the plan, and this is a little bit of a handwave, Artemis 2 is still slated to take place in 2024, and I have so much trouble with that, because 2024 is literally next year, but they think it'll happen in November. So November of 2024 might become a regular This Week in Astronomy and History if it goes ahead. Of course, in Artemis 2, they are planning to actually send a crew, and we have a Canadian astronaut who has been approved to go as well, which is Jeremy Hansen. And a lot of you might have seen him recently on the news, visiting places around Canada. I'm hoping he comes close enough we can get a picture at the observatory, but we'll see. So anyways, this week in this history, very exciting race to the moon, I suppose.
Absolutely. So we have about 8 minutes left. We are kind of nearing the end of our time. I was wondering if you wanted to move on to a couple news items before we finish off.
Yeah, that might be a good idea. Let's go ahead and make sure we cover at least Bennu.
Absolutely.
So Bennu has been on a lot of people's space news radar for a while. And Bennu, if you hadn't heard or maybe somehow missed the incredible excitement earlier this year when the sample returned and they were showing it live on the news, it was super exciting. The sample return capsule came back to Earth. They had helicopters out in the desert waiting to waiting to get the chance of where it would land. And then as soon as they got the landing site confirmation, everyone ran into the helicopters and flew over. And the rest of us got to watch on TV. It was very, very exciting. So since that sample has come back, of course, the asteroid Bennu, which the sample was taken from, has become a hot topic. We're learning more about asteroids and Bennu-like asteroids in particular. If you haven't somehow heard of this asteroid yet, let me just tell you a little bit about it. It's not a particularly large asteroid. It was discovered back in 1999. It is a near-Earth asteroid, which is one of the reasons why we're interested in it. And it's not large enough to pull itself into a sphere. So it's thought to be, fairly fairly low mass. I don't know if 7 times 10 to the 10 kilograms means anything to anyone, but about something like 500 meters by 500 meters by 500 meters. So it's not gigantic. It's certainly large enough you wouldn't want it to hit you, but it's sort of shaped like kind of a very rough diamond. It's got kind of that that same diamond shape that you see on card decks. It's an interesting object. It sort of seems to be throwing off little tiny pieces of itself as it spins around. It's very, very low density. It doesn't seem to have really been messed with at all since potentially the formation of the solar system. So the news item, there have been a lot of news items about this, the sample getting taken to the labs, how many grams Canada is going to get, because of course we will get assigned some because we're part of this mission. The sample brought back was, basically just a very, very small little piece of rock. I think it ended up being something like the 200 grams, although I forget the exact sample size. And right now, the Smithsonian has recently debuted the very, very first actual display piece. So they're trying to share it as much as possible with everyone, although they're also trying to, as much as possible, prevent it from having any contamination whatsoever for scientific experiments. So a very, very small part of the sample was unveiled recently on November 3rd, just a couple days ago, at the Smithsonian National Museum of History. This is the Hall of Geology, Gems, and Minerals. So it's actually inside a stainless steel bottle with a little glass viewing port. And the rock that they've selected is very, very, very black in color. And it's enveloped in a pure nitrogen environment to keep it pristine and to hopefully prevent it from being contaminated by other things. So at the museum, they do have a model of the OSIRIS-REx, which was the spacecraft that actually went to Bennu. So the OSIRIS-REx was the mission. And again, we could probably talk about that just for a whole nother hour in and of itself, because it's still going. It's actually going to arrive at the asteroid 99942 Apophis in 2029. So the OSIRIS-REx spacecraft has done great work for us, bringing this sample back, and you can go see it. It's a very small piece of rock, very black, in a display case. The number of people who turned out for the unveiling on November 3rd was tremendous, apparently. So I don't know if you'd want to be part of that original, tour group. The stone itself is 0.3 inches in diameter, or 8 millimeters, and 0.005 ounces, or 143 milligrams. So it's a stone out of the sample. It has been CT scanned. So just like you can go to the doctor to get a CT scan, they can actually CT scan, well, in this case, a rock, to show that the stone is made up of lots and lots of smaller fragments. So it's been broken up in its past, and this little piece was then sort of cemented back together, may have been altered by water. There were some clays, iron oxides, iron sulfides, carbides, minerals, carbon. And it was selected based on a few criteria, basically that it was durable and photogenic, being flat or relatively flat, and it had to be able to fit in a display container, which is also pretty important. The Smithsonian has another piece which they're not going to let anyone see, and that's for scientific studies. There are 2 other displays if you're not near the Smithsonian, but unfortunately, none of them are particularly close to Canada, and especially not Toronto. So the University of Arizona and the Space Center of Houston will have 2 other displays for Bennu rocks. So it is actually possible to share at least a little bit in this latest Bennu adventure. The asteroid and the sample return have been incredibly exciting, and of course, Canadian researchers can continue to be excited because we'll still be getting our pieces of Bennu to study. I say ours, but I'm not actually going to get one. And if you would like to see Bennu, all you need is a very, very, very big telescope, say about 1 meter in size, like we have. I will just point out, Bennu is actually observable just before the sunrise in Toronto right now. It's magnitude 22.65, and you have to get out there at about 4 or 5 in the morning before the sun comes up. And you will need to take a very long exposure with basically a 1 meter telescope or equivalent to see something that dim. But you can yourself track Bennu across the sky if you want to. So look forward to that coming out of the observatory archives soon, I suppose.
All right. Well, with that said, what an exciting note to end on. We are at the top of the hour now, so I have to say, you've been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Elena Hyde and myself, Quentin Weyrich. You can always connect with us on Twitter with the handle @YorkU Observatory, @York Universe, and on Instagram with the handle @YorkU Observatory, and Facebook @Allan I Carswell Obs. Check out our website for show notes, content updates, and contact info at www.yorku.ca/science/observatory. Thanks once again for tuning into York Universe. Clear skies and have a good night.